Thank you very much for your kind introduction. I'll be talking about climate change, science and policy aspects of it, but I will spend a few minutes first just talking about stratospheric ozone, what led to the Nobel Prize that I was rewarded with. It was, of course, a huge honor to receive it. I should just say, I gave a similar lecture yesterday. I know there are just a couple of you that heard me already. I thought I could give a different lecture today, but the only way I could do that is if I give it in Spanish. So I apologize, but I'm actually going to use the same or similar view graphs. So what I want to do is to put in context the research that I carried out with my colleague Sherry Rowland. We were at the University of California at Irvine. This was in the early 1970s. And at that time, I had just finished my PhD at the University of California at Berkeley. But I had met Sherry Rowland already because we were both doing very fundamental research on chemical reactions, trying to understand chemical reactions at the very fundamental level using quantum mechanics and so on and so forth. But we both decided when I came to work with him to work on something that was a little bit closer to some societal problem, to something that which we could apply this fundamental science understanding that we had developed. And so we decided to learn about the atmosphere, to do atmospheric chemistry, which at that time was not a very well-developed discipline. We had a few colleagues that we had met that were working on that. But what we decided, let's work on how do we do that? Let's work on a problem that we think it's interesting out of sheer curiosity, see whether we can solve it, and in that way learn about how the atmosphere functions, particularly some of its chemical properties. So that's how we started. Let me give you sort of a little bit of the background. And this is going a little over a century ago, how electric refrigeration became to be of course, very common, very useful, first in developed countries, but then eventually everywhere. And that's using electrical refrigerators. Now, some of you might know before that, how did people deal with refrigeration? Because that was already in use in the 19th century. But it was typically only more wealthy people, but there was a big industry that had been developed. The way it worked is by importing large chunks of ice from frozen lakes at northern latitudes. That's the way refrigeration worked before the electric refrigerators came on board. And so it was maybe easier to have refrigerators here at these latitudes than it was in Southern California or in Mexico, okay? But so, nevertheless, this worked very well. How does a refrigerator work? What you need a refrigerant, which is a fluid that with this electricity, with an electric motor, you can compress it as a liquid, and then you make this liquid move through the freezer and evaporate. As it evaporates, it cools. And then the gas that is formed, you compress again to form a liquid and so on. So it's a very simple idea. There are other ways to do that, but this was a very effective way. But it had a problem, namely that the refrigerants that were in use originally were sort of nasty chemicals, sulfur dioxide and ammonia. And so there were a number of accidents when home refrigerators broke down and leaked, and people had to breathe these gases. That was, of course, it led to some accidents. And so chemists developed new chemicals. They were called at that time miracle chemicals that could be used as refrigerants, but in some way not poisonous. And so the chemical industry developed these so-called chlorofluorocarbons. You can see here the formulas. But the important thing about these chemicals is that they are very inert, very stable. They also evaporate, and so they can be used as refrigerants, but you can breathe them. They are so inert that they don't change. You can breathe them and nothing happens, certainly as opposed to ammonia. And because of that, they could be used also as propellants in spray cans, which you certainly cannot have something like sulfur dioxide, because it would be a little stinky, okay, but also very harmful. And the spray cans became very popular, particularly in the United States, because many things were sprayed, from toothpaste, cleaners, and so on. And so that's how this problem arose, because we had a colleague, Jim Lovelock, who had developed a very special instrument, an electron capture gas chromatograph, and he was able to measure the presence of these CFCs, these refrigerants, in the atmosphere. It turns out not just in the northern hemisphere, but even in the southern hemisphere, where they were actually not produced. But clearly, these compounds were mixing all over the planet. That's why we have a global issue with these compounds. Well, I'm not going to give you a lot more details other than Sherry Rowland and I then decided to investigate what's the fate of these compounds in the environment. And we realized they were very stable, and they were going to eventually to diffuse into the stratosphere. That's a layer above the troposphere, the lowest layer that we have in the atmosphere, at sufficient altitudes so that just like molecular oxygen, or O2, that we all know, at high altitudes, solar radiation of very short wavelengths breaks the molecule apart and making oxygen atoms. So the CFCs at sufficiently high altitudes would also break down and release chlorine atoms. And what we then sort of postulated, because we knew that from fundamental chemistry, is that chlorine atoms react very fast with ozone. And the product, chlorine oxide, reacts again, so you recover the chlorine atom. So the bottom line is that we have a catalytic cycle. A single chlorine atom, which is recovered with this mechanism, can destroy tens of thousands of ozone molecules. And what's ozone? Ozone is formed again by the breaking molecular oxygen, but it makes this layer, the ozone layer, in the stratosphere, 30 to 50 kilometers sort of above the surface mainly, but it shields us from short wavelength radiation that comes from the sun that is very harmful to a number of living creatures, but among others ourselves, humans. If you get this short wavelength radiation in your skin, it breaks down DNA. There are some repair mechanisms, but sometimes they don't work well, and you get skin cancer. So that's one of the issues that happen if you affect the ozone layer. And so that was our theory, but we based it, our colleague Paul Crutzen, with whom we share the Nobel Prize, he had earlier sort of discovered or suggested how the natural ozone layer is controlled, and that's with natural amounts of nitric oxide with a similar catalytic mechanism. And so we were able to also work with him and with the other members of the scientific community that knew or that were working on the stratosphere. And essentially it appeared that the science was well understood. And that's why we then published a paper in Nature suggesting that the release of chlorine atoms would eventually deplete this ozone layer, and that it's something we should try to avoid, not to get a large health problem for humanity and for other species as well. But it turns out, although we had not anticipated it early on, but over Antarctica, something very special was happening, something very spectacular, namely, only over Antarctica, in the spring months, which is September, October, in the southern hemisphere, the ozone layer was beginning to be affected, not in the first few years, which was in the 1970s when we first came up with these theories, but in the 1980s. Now we understand why, because it's a very non-linear effect. I won't bother you with the details of the chemistry, but it's two chlorine monoxide molecules reacting with each other, so the effect is proportional to the square of the chlorine concentration. But what happens, you can see here, is in a matter of weeks, over Antarctica in the spring months, and again, only starting in the 1980s, not before that, ozone was disappearing, but quite fast. And at altitudes where it's normally most abundant, more than 99% of the ozone was reacting away. And so that's what we now label the ozone hole. And over the Arctic, something happens, but not quite as dramatic. We now understand why, because Antarctica gets much colder, because the topography of the planet works in such a way that the polar vortex is much more stable in the south, where you have a continent of high altitude, but surrounded by flat oceans, whereas in the north, it's the other way around. You have a flat ocean, which is normally ice, surrounded by continents, so the vortex is not as stable. And the bottom line is that Antarctica is a place where the stratosphere, and in fact anywhere close to the surface, is at the lowest temperature, minus 80 degrees Celsius or so. And we also now understand how the chemistry, some ice particles form that accelerate this destruction. So the science became very well established. We had some measurements that indicated really with a lot of confidence that it was indeed the CFCs that were causing this problem and not the natural effect. But what was particularly encouraging is that we started, even before the ozone hole was there, we started to work with not just with the scientific community, but trying to communicate this problem to society. Because I remember Sherry and I sort of asking ourselves, what should we do now that we face this global problem that might have some social consequences for society? If not us, whom? If not now, then when? So we went all out and communicated that, most importantly, to decision makers in government, to the public in general, and eventually also to diplomats. And fortunately, we were able to convince heads of state, and through the United Nations, an agreement was reached, the Montreal Protocol, in which practically all the nations in the planet agreed to stop manufacturing these chemicals. And by that time, the chemical industry very much agreed with us as well, and they were producing other chemicals that we now use as refrigerants. You don't have to use CFCs anymore. And because of the Montreal Protocol, we now know that the ozone layer is recovering. It's a slow process because the CFCs are still damaging the stratosphere, those that were emitted in the 20th century, because they remain in the atmosphere for many decades. But clearly measurements are indicating that the ozone layer is already recovering. So we have a very big success story with this issue. So let me now switch to climate change. And I'm going to start again putting this in context with sustainable development, which is, as you can read it here, it's development that meets the need of the present without compromising the ability of future generations to meet their own needs. That was put up by the Brundtland Commission, Ms. Brundtland being Prime Minister in Norway at that time. And what I would just correct now is that sustainable development nowadays also means worrying about our own generation, because we're already seeing happening not just problems for the future, but problems that are affecting us nowadays. And before I start with climate change, give you just some indication that there are many other problems. The scientific community has identified at least 8 or 9 problems that they call parts of the planet boundary, namely issues that affect the entire planet that we should be worrying about. But what is interesting is that if you look at industrial development, you look at how, particularly because technology advanced a lot, it is in the second half of the 20th century that industry really suddenly began to develop very fast. And one of these issues is the release of carbon dioxide, which results from burning fossil fuels. But this is a consequence of all these changes in economic terms: population, GDP, fertilizer consumption, paper production, what have you. At least all these issues, there's something peculiar that you can see that these curves bend. And that's why this is called the Great Acceleration, starting roughly 1950. Okay? And these are the changes that worry us. What are we doing to the environment? We're certainly, we were affecting the ozone layer. That's one thing we have dealt with. But many other problems we have not dealt with, climate change being perhaps the main one. But because of these changes, our colleague Paul Crutzen in particular has sort of put on the table this issue that we are in a new geological era, which is called the Anthropocene. Okay, we no longer live in a geological era like in the past, where the changes had to do with periodic changes, perhaps in the Earth's orbit that causes ice ages or large volcanoes erupting or what have you. The big changes nowadays clearly come from human activities, hence the name Anthropocene. Okay? Yeah. And one suggestion is that this new era really starts around 1950 because of this acceleration that I just pointed out. Anyhow, there are issues besides climate change, such as the nitrogen and phosphorus cycles. One very worrisome one has to do with species disappearing. Okay, so we have historically something like 5 big extinctions where many biological species disappeared because of something big happening, like a large meteor landing somewhere close to the Yucatan Peninsula in Mexico, and that's what killed the dinosaurs. Okay? So some huge events happened in the past, but now we have the Anthropocene, and it's one important cause for this biological disappearance of many important species. But I will not be talking about these other issues. Let me concentrate on just climate change, and I'll do that by talking about these 3 myths. These are 3 points in which there is some misunderstanding, particularly by the general public, but also by many politicians. The first one is the idea that, climate is very complicated. So maybe some scientists think that something is happening and we should worry about the climate, but many other scientists believe that's just natural. Climate, after all, has changed in the past. So it's not clear that it's due to human activities. That's a myth. Why? Because surveys have been carried out very explicitly, really measuring what the experts think, not what people in general, or even the scientific community in general, but people that work in some way, whose scientific work is connected with climate change. They've published papers, and the vast majority agrees. Climate change is certainly taking place, and it's different from the changes that we have had in the past, and it's most likely a consequence of human activities. Okay? So that's what is very well established, and when I show this, I like to expose that when these surveys were done, there was this 3% of skeptics, if you want, is not the right word, because we all scientists are skeptics. We don't accept new thinking in science until it's very well corroborated. Science, after all, goes with measurements and with reasons, okay, with the scientific method, where you sort of establish whether something is happening or not based on experiments that are reproducible, and so on and so forth. But that has already happened with climate change science. So there are no good explanations of what's happening today other than the accepted science. And the point is, we understand very well what the objections are from these 3% of, now smaller, I believe, of scientists that really question this. But I insist that there are many scientists that still don't believe in this, but because they are not experts and have not looked carefully at what's going on. But I like to point out one of the main ways in which the non-scientists or scientists in different specialties or politicians, they point out, oh, something must be wrong with climate science. They don't take into account that climate is a complex issue, just like the human body. Okay, we are complex, and that's why medicines don't work 100% of the time, because some of us are different, and so you have to talk about probabilities and so on and so forth. And you might have sometimes a very good theory, but things remain to be explained. The same thing happens with climate. Not all aspects of climate are perfectly well understood. The role of particles, for example, there are still some questions there. The role of clouds, how exactly do they compensate for climate change? These are things which require additional science research to be carried out. But it's in general well understood. But the people that object, sometimes they do what we call cherry picking. They find something wrong. One aspect, I mentioned two possibilities, but there might be some measurements that were questionable or what have you. And they somehow or other make an analogy that the science of climate change is like a house of cards. And if you find one card somewhere that doesn't quite fit, remove it, the whole thing falls apart. That's cherry picking. That's not the way science works. It's more like this, like a puzzle. And we have pieces of the puzzle that we still have to fit together. But you can more or less figure out what's there, which is not a very sort of harmless little kitten, okay? So the bottom line is that the science is very well established. And so I'll tell you briefly a little bit about the science itself. I'm not going to have time to go into much detail, but first I want to highlight, we're talking about a global problem. And it's a problem with the atmosphere, which you cannot see because the atmosphere is transparent. But it's also very thin. I like to make the analogy, it's like the skin of an apple, because most of the atmosphere is close to the surface. Above 50, 100 kilometers, it becomes so thin that it doesn't affect climate in any significant way anymore. But if you release some chemicals like carbon dioxide or CFCs that are both very long-lived, carbon dioxide, in fact, it has been measured that some fraction of it remains more than a millennium before it somehow or other gets absorbed again at the surface. And so half of the carbon dioxide that is emitted is absorbed relatively rapidly, but a good fraction of it remains in the atmosphere for a long time. And the CFCs, that goes back to our original findings, remain many decades before they can get into the stratosphere. Anyhow, because mixing within each hemisphere takes place on a timescale of a few months, that's why we talk about global problems, because it doesn't matter where these gases are emitted. They mix it throughout the entire planet. And the stratosphere, the ozone layer there, covers the entire planet. And the climate, even though it varies, of course, its consequences are local. we're talking about global climate when we're talking about these issues. That's the problem. But what's happening? Well, let me just explain very briefly here the following reasoning that was already what scientists were dealing with in the 19th century. The question at that time was, how does the climate of our planet come about? And the reasoning was, look, we can measure how much energy does our planet receive from the sun, and that's what's keeping us warm. And we know from physics and from some of the laws of thermodynamics, what have you, without going into detail, but already for millions of years, our planet is in thermal equilibrium, namely, it absorbs energy from the sun, but it emits the same amount of energy it receives. It's no longer accumulating energy. There's some energy inside the planet, but it's very well insulated from the surface, so it doesn't affect climate, except when you have huge volcanic events. Okay. So here in this graph, we have a plot of this energy which comes in the form of electromagnetic radiation, visible radiation. Our eyes evolved to see light from the sun. And at much shorter wavelengths is infrared radiation, which is how our planet loses but the same amount of energy. And you know, of course, that warm bodies emit radiation. We can measure it in the lab. And as you increase the temperature, eventually they can become red hot. That's when they begin to emit some visible radiation, already very warm, and white hot, like in incandescent bulb. Then it's really very high temperatures, and the sun is, of course, at very high temperature. But fortunately, we're not that warm. That's why life could evolve. And infrared light emitted by our planet is not visible. And so you could measure that in a laboratory and measure the dependence of these energies on temperature. And the answer that was first obtained by doing this balance is that our planet should be at around minus 18 degrees Celsius. That would be a frozen planet. We wouldn't be here. So that's not the case. Just to explain that this initial finding of what the temperature was wrong, because the atmosphere, however thin it is, functions as a blanket. And this blanket keeps some of this radiation coming from the surface, as I explain in a minute. But I forgot, I wanted to first explain, this is just a little bit a side issue, but very interesting one, that these measurements that were carried out could not be explained early on in terms of how much infrared radiation bodies emit in the laboratory or a planet in space. And it was Max Planck, that was able to rationalize these equations and explain them in physical terms. And that's what I have in this view graph. This is Planck, and that's the law that he was able to explain how by inventing nothing less than quantum mechanics. You can only explain those observations by assuming that energy comes in packets, light comes in packets as well, called photons. That's Einstein also helped with that. And so this revolutionized physics, of course, solid-state physics now, and chemistry, quantum chemistry nowadays, biology and so on. We had an enormous change in the sciences towards the beginning of the 20th century. But this all only partly sort of affects the way we understand the climate, because it was, after all, already well measured in the laboratory. But the point is the following, that we do have a blanket. How does this blanket function? If you look at these three arrows as energy coming from the sun, one of those arrows does not absorb by the planet. It's reflected by clouds or by the surface. You can have light surfaces like snow or ice, or you can have deserts like the Sahara Desert. They reflect light. But about 2/3 of the energy that comes from the sun gets all the way to the surface. And the atmosphere is transparent, except for the clouds, of course, that reflect it. It's transparent to visible radiation, so it makes it all the way to the surface. But then I was explaining that at the temperatures that we have, the surface then emits, in principle, it would be the same amount of radiation, except that we do have this blanket. And because the atmosphere absorbs this infrared radiation, it has to emit about twice as much, because since the atmosphere absorbs it, then it re-emits this radiation, the molecules in the atmosphere absorb it, then they re-emit this energy in all directions, roughly half upwards, half downwards. That's why you have to, the surface has to emit about twice as much. Half of that comes back to the surface, warming it up, and only the two remaining arrows is what goes out to space. And so in principle, you're not accumulating energy anymore. It has already reached equilibrium long time ago. But this explains very clearly how this blanket functions. Okay, that's the greenhouse, the natural greenhouse effect. Just one more piece of information, interesting, which is an atmosphere is mostly nitrogen, oxygen, and a little bit of argon, just about 1% of argon, which is an inert gas. And these gases are all transparent, not just to visible radiation, but also to infrared. So it turns out it's only the tiny amount of gases whose molecules have more than 2 atoms, like water vapor, H2O, of course, you know, CO2, and a few others like the CFCs. These are the gases that do absorb infrared radiation and then give it the property of a blanket. Water vapor absorbs about 3/4 of the radiation emitted by the surface, and carbon dioxide, most of the rest, but there are these other gases besides the CFCs. There's methane and there's nitrous oxide. But the point is that it's only small amounts. They are measured in parts per million levels. The amount of CO2 that you would have if it were condensed rather than in a gas phase would just be a 4 millimeter thick dry ice sheet. Okay? And that's what keeps our planet nothing less than 33 degrees warmer than you would have in the absence of these gases. That's the natural greenhouse effect. But something else happens. The amount of water vapor depends very much on temperature. It condenses, water evaporates from the ocean. As it goes to higher altitudes, the temperature drops, and the water in the atmosphere, as originally as a gas, as a vapor, condenses to make clouds, rain, snow, and so on. So if the point is the following, it's carbon dioxide, although it's responsible for only the remaining 1/4 of this balance. If you were to remove carbon dioxide, the atmosphere would begin to cool and water would condense. And here is what would happen. Clouds, you would get a lot more of the water vapor condensing, coming back to the surface, and you would get a frozen planet. So carbon dioxide is the thermostat of the planet, and that's very well explained also in geological timescales for ice ages and so on. This is sort of, I just gave you a brief glimpse of the physics and of the natural climate, okay? Just to emphasize that it's well understood. But now let's see what humans have done. And here we look at this graph where we have carbon dioxide for the last 10,000 years, which is the Holocene. That's the geological timescale during which human civilization has really advanced. That's when agriculture was founded and so on and so forth. Before you had ice ages and more complicated climate that was not, you had hunter-gatherers before that. Agriculture just came in this time period. And for this time, the carbon dioxide amount was less than 250 parts per million. And if you go back even millions of years, it was always around those levels. And suddenly, on this time scale, it jumps. And it's now at least 40% larger. And it's not long before it's going to be twice as large as this has been for millions of years. What's happening? That's because you're burning fossil fuels. Where do the fossil fuels come from? That's from photosynthesis. You remember this cycle. You have oxygen in the atmosphere and carbon dioxide as well, and water vapor. And green plants can take carbon dioxide, water vapor in the plant itself. Through photosynthesis, it makes food, carbohydrates that we can eat. And as we eat them, we can use them to generate energy. How? They get oxidized, and this chemical energy is what we can use to walk, to run, and so on and so forth. And what's the result of that oxidation? It's you get back the oxygen and water vapor. Without photosynthesis, we would have run out of oxygen. Well, this extra CO2 comes from photosynthesis, but that took many millions of years to take place, and those plants, some of those decomposed below the Earth's surface, giving you coal or petroleum. Okay. Oil. Okay, so there are lots of details known about that, but that's what happened. And if we see what's been happening to temperature, not easy to measure, but it's very clear that you have a similar jump. Just in recent years, the temperature has jumped about 1 degree. Doesn't look like much, but we're talking about this average surface temperature of the planet, which doesn't change very much with time. We have a little cooling from the year 8,000 years ago. That might have continued, but long before we get an ice age, that might take several tens of thousands of years if we were to continue that way. And suddenly we jump upwards to a temperature that we haven't seen for a long time, okay, for tens of thousands of years. And of course, the question is, given all this explanation about the science of the climate, they should be connected. But how do we evaluate that? And one way to do that is there's a group of scientists. They get together. There are voluntary scientists. And about every 5 years, they publish a report. That's the Intergovernmental Panel on Climate Change, the IPCC. They write a report summarizing the science. And their conclusion is that, indeed, we're not quite sure that the temperature change is caused by CO2. We only can do that, can make statements in terms of probabilities. And the probability with the last report claimed by this group is about 95%. So there's some possibility that the climate is changing just because by chance, 5% probability, but the most likely thing is that it's indeed caused by human activities, okay? So that's the science itself. But let's look at the next myth, namely that we shouldn't worry about this. This is just something that our children, perhaps our grandchildren, need to be concerned with because climate changes very slowly. Well, that's not really the case. The Arctic Sea is already melting, okay? And much more worrisome, perhaps, is that we have extreme weather events, heat waves that are already killing many people, and we have also hurricanes, floods and droughts and wildfires and so on. And in the United States in particular, we saw last year, 2017, economic losses of the order of $3 to $4 billion just caused by these events that we call extremes, climate extremes, okay? And if we do the statistics, I just plot a few here, there are many more, but they are all increasing. So what does science have to tell us about this? Science very cautiously, as near as 10, 15 years ago, say, well, let's wait until we have good enough statistics. But now it's very clear. There is indeed a connection, and the connection is probabilistic. These weather events were not caused by climate change. You would still have hurricanes, they have happened for some time now, but it's the intensity of these events, that's why we call them extreme events, that has very clearly increased as a function of time. So so much for that myth, but the last is a very important one. Why should we worry about fossil fuels, they are so important for the economy, we cannot really touch that because that's how what our economies depend on fossil fuels. Well, that turns out to be a myth as well, because now we have other ways to generate energy. Of course, electricity, now it's well known, this is relatively recent, just in recent years, the technology has advanced to such a degree that now these forms of energy, wind and solar, are competitive in economic terms with fossil fuels. Of course, it's difficult to change society. That's one of the difficulties for them to change fast because investments have already been made. But the point is that we can already do it, and we don't need to sacrifice economic growth. And these sort of energy forms also generate a lot of jobs and so on. So there's no longer an excuse that you need to subsidize this change. It is economically competitive, okay? Of course, there are still issues that require further technological development, such as these are intermittent. So, of course, solar energy only works during the day, not at night. Wind energy sometimes doesn't work. But there are lots of technological advances storing these energies. Okay? And there are already some that are working and many more that are being developed. So we can do it. Okay? And the question then is, what has the world done about this, which is perhaps the most serious challenge that society is facing, certainly the most serious environmental challenge, but in terms of what might happen in the future. And the good news is that, to begin with, we had a meeting which is organized by the United Nations. These are so-called the Conference of the Parties. Already in 2009, I was there in Copenhagen, and there were more than 120 heads of state at that time. And they all agreed. There was consensus. We need to do something about climate change. Heads of state all agreed all over the planet. And one way to sort of condense these goals was to say, let's agree that the temperature of the planet, we should try to keep it from rising 2 degrees. It should hopefully rise less than 2 degrees Celsius. I remind you, we're already halfway there. Okay? And even if we were to stop emissions now, because the planet is not yet in equilibrium, the temperature would continue to rise for a while. So we're not that far, but that's what the heads of state agreed, but not, unfortunately, the people actually doing the rules, the negotiators did not agree. So not much happened in Copenhagen. But we kept working very hard. And finally, in December, in the 2015, the Paris Agreement came about. All heads of state, I was there, in fact, this time more than 150, they all agreed to try to reach this goal, to begin with, perhaps not with measures strong enough to really reach the degree, but each country coming up with voluntary measures to reduce their emissions, and with the idea that they would meet again in 5 years, so in a few years that will happen, to explain what else needs to be done so that the climate doesn't keep changing, okay? And of course, it's going to be measured and so on and so forth. So that's an incredible achievement, which means it's just like the Montreal Protocol, but it's only halfway, and it's only on its way. But here is what's happening. If we look at emissions as a function of time, we see that the 2 degrees line is the blue line. We are not there yet. We will have to reduce emissions much more dramatically. The Paris Accord is sort of halfway. If we do only the Paris Accord, we might get all the way to 3 degrees, who knows. But if we do nothing, that's a big worry. That's the red line. We could reach 3 or 5 degrees, okay? And so, what should we do? There's another very big worry here in the United States. There are many states, California, Massachusetts, and so on, that very much agree with this, but not the central government. President Trump, as you know, does not want to remain on the Paris Accord because he does not believe in climate change. Wow, that's a big worry. Let me just tell you, what does that imply? And so I'm going to show you Eustace Roulette, which is one way to explain that to the public. You don't have to be a scientist to understand this. And this came out of the MIT group. I was many years at MIT, so worked with this group at the Global Change Center. They have a very large, one of the most complete models of the climate of our planet, which is coupled to a very large model of the economy of the entire planet. Okay, and the left roulette corresponds to the red line in the previous graph. If we just continue without worrying about climate change, temperature might change 3 to 4, but there's a red portion there. It might change more than 5 degrees. Wow, and that's a very big worry. But we can change. This was done before the Paris Agreement. I need to put it up to date. But the point is that if all the countries in the planet agree to do something, we can certainly avoid the red zone. Okay, and that's what the scientific community is trying. I think the most important message is not necessarily what's the most likely change, but the fact that if we continue without measures, we will reach temperatures that have not been reached in our planet in more than 50 million years, when there was no civilization, no people around that time, and it was an entirely different planet with crocodiles in the North Pole. But that happened in tens of thousands of years as a result of huge volcanic eruptions, very unusual in the climate history of our planet, 55 years ago. 55 million years ago, sorry. But if we manage to do that in just a few decades, what would be the consequences? We would have portions of the planet uninhabitable because of the heat waves. Okay, people cannot survive in places where the temperature is 50, 55 degrees centigrade. We would have massive loss of agriculture. How do you feed the 9 billion people that are going to live in the planet at that time? You would have massive migrations. All these extreme weather events, some of them could go wild because you have many non-linearities in the climate. So the bottom line is that we label this as an extreme irresponsibility, okay? Because science is well established. We're not talking about certainties, we're talking about risks. This is a huge risk. 1 in 5, okay? 1 in 10 is already totally unacceptable. I just pointed 2 or 3 things in 1 or 2 more minutes. But here is one of them. How did it come about that so many people do not believe in climate change? There are, of course, some issues that have to do with the Republican Party I'll mention in a minute. But first this. It turns out Naomi Oreskes is a historian. She was at the history department in San Diego, where I'm lecturing nowadays, but she's now in Harvard. And she published a book, and there's now even a movie, just documenting how some interest groups have to do with a couple of fossil fuel industries. They had a lot of resources. It was not interested themselves, but some of the people financing, a couple of billionaires that we have here in the United States. They put a lot of money in not just trying to affect the elections, which they did very successfully in certain places. They put a lot of money on the elections themselves, but they put a lot of money with the news media trying to discredit climate science. And that's not new. That had happened. It's the same company had done that already with smoking. You know that it's well known that for many years now that smoking, and not everybody that smokes will suffer, but it certainly can affect your health. But these companies managed to put doubts in where there were juries and so on and so forth, so that governments did nothing about smoking up until a decade later than science had already established that. Okay, so that's one aspect. But it turns out, unfortunately, I already mentioned that the Republican Party just does not believe in this. They sort of fell on this trap, but it's no longer an excuse. The science is very well established, and so it's no longer acceptable. And we have this huge population. We need to do something about it. But let me just finish. I'll give you one example. What does a 1 in 5 probability mean? And we sometimes, I'll just summarize it. I fly a lot because I give a number of conferences and so on. And occasionally the pilot comes on board when you're already on the plane ready to take off and say, we're sorry, we have a technical problem. We're going to have to fix it, wait, might take a couple of hours, but we just need to fix it. But I had once a very adventurous pilot who said, we have a technical problem. I know we would have to spend several hours to fix it, but I know you are in a rush, so don't worry. We're going to take off anyhow. Don't worry. Only 1 in 5 probabilities we won't make it. Okay. Who would climb? Thank you for your attention.
Thank you very much indeed, Mario. Hi, I'm Adam Smith from Nobel Media, and it's my pleasure to moderate now a Q&A session with Mario after his lecture. We have some time for questions, and I do hope you'll take the chance to ask some. And there's a hand gone up already. I love it. Great. So please, fire away. Mario, if you're ready.
Yes.
Hi. So yesterday, one of the panelists said that there were numerous grand challenges that we need to face in order to survive as a species. And climate change was special in that it managed to enter the consciousness of the general population. And my question is, what do you think that the climate science community did that allowed it to make so much progress compared to potentially other branches that did not succeed as well?
Let me make sure I understand the question. Is it why climate change is special?
Yes, why is climate change special in public consciousness as opposed to all the other grand challenges? It's the one that really has touched the public.
There have been a few efforts by the scientific community. I've been part of a few of them. I mentioned one, which I didn't have time to explain here, which is this one of planetary boundaries, in which what they're trying to talk about is problems that affect the entire planet. Of course, you have a lot of local problems. Air pollution is one of those. But in terms of issues affecting the entire planet, they have been identified by this group, and then many others have published around that, and just established, trying to measure what's wrong and what can we do, and so on and so forth. Well, it turns out that some of those worries are not yet sufficiently well understood, and they remain to be further investigated, and scientists recognize that. They have to do with chemical pollution. There are certain chemicals that are known to affect locally very harshly the environment, but how is that going to spread out? That's one issue. Other things like the phosphorus cycle, yes, we can do something about it. We're using fertilizers far too much, and it causes dead zones in the ocean. So anyhow, the point is that one of the most worrisome, but I would say clearly the most worrisome one, is climate change, because we're already seeing enormous damage. It's costing to the United States itself between 2 and 3 billion last year just for the hurricanes, and another billion because of the forest fire. So you can actually measure the damage, but with a warning. I'm a good friend of Nick Stern, who's an economist that has been very active quantifying the damage, and he had some economic measures early on that helped with the Copenhagen Accord and so on. But one of his last reports, I very much agree with him, is that the damage has been grossly underestimated, and you cannot measure it in dollars only. How much does it cost to have 300,000 people perish in a heat wave? what's the cost? Well, it's a moral issue. So I want to stress, perhaps this is my opportunity, I should have done that. Science doesn't tell us what to do. Science only tells us what would happen. But we have moral commitments, we have values, and we want to make sure that future generations have the same options that we have in this generation to have a reasonable standard of living and so on and so forth. So that's why climate change is a huge issue, because we're talking about enormous changes in society, okay, that can be well documented. And if one issue where science is very well established, we're not making progress, what do you expect of the other issues? Now, fortunately, air quality is just a good example of something that we can mix with climate change, as is happening in China, in Mexico as well, and so on. So at the same time that you fix the air, you fix emissions by not building more coal-fired power plants, for example. So that's one response, but the science is sort of tells us, it doesn't mean we should only worry about climate change. That should be clear. We have to worry about everything whenever it's time.
Thanks. Can you just wait for the microphone? Thanks.
Yes. Question I have is there is indeed a great deal of consensus about the effect of climate change. To me, it doesn't seem that there is the same consensus about the solution. There's a lot of people who believe that the use of renewable energies won't work. I'm sure you're familiar with the paper that was put out by the American climate scientists, who said that one of them used a pejorative term about renewable energy believing in the tooth fairy. Jim Hansen said that. And my point is, how do we decide which is the right track when there are some people telling us renewable energy is the correct path, and the other one is saying, no, we've got to use alternative, particularly nuclear energy?
Yes. Well, let me give you a couple of answers. First, that was an unusual paper. It has been debated, and I believe it by many industries, let alone scientists. It's many industries that are specialized in energy, even fossil fuel energy industry, disagree with that, because it's very clear. You can see the percentage of energy coming from these renewable sources increasing rapidly. But most importantly, that's what is not taken into account there, is that the objections, they are not that difficult technologically. Okay, so there is a sort of consensus that engineers, I happen to be a chemical engineer myself or so, but engineers will be able to solve that. The problem is political. Okay, so it is possible. But nuclear energy certainly should be on the table. That's much more debatable. You see what happened in Germany. But again, much of my what I know about the energy perspective of it, I get from MIT, because I'm part of there's an MIT Energy Initiative, and they have a board with many people from industry. So I get not just the academic perspective, but also industry's perspective. Okay, and the view there is that, I repeat, that renewable energy is advancing very fast in spite of just a few papers. Okay, most others don't agree. But nuclear energy also is advancing a lot. I know that it's worrisome what you do with waste, but the amount of waste is very small. So that's a soluble problem. It's a political problem, where do you put it? But in principle, it's technologically, it's something that you can deal with, okay? It's just, the political is complicated, but it's the fourth generation nuclear, the cheaper, smaller nuclear reactors that are probably going to be relatively cheap. And if indeed there are problems, there are limits, should there be limits to the conventional renewables, that will be able to help. And there's one more point, just to mention it, which is we waste a lot of energy. Okay? And we know that in some places, the Scandinavian countries waste a lot less, and they have a very acceptable standard of living. So we can do a lot better without incandescent light bulbs, with efficient air conditioning, with much better insulation. So these technologies are around the corner already, and some are already implemented. Okay, so that's yet another way in which the solution comes about. But given the cost of not doing anything, clearly overwhelms the cost of the solutions that are in the horizon already.
Thank you.
That's the way I would put it.
Okay.
Yeah.
You next, and then you, and then we'll.
Okay.
Yep.
Oh, they have the microphone on.
Yeah, I'm. Yep.
Hi, I'm just wondering, so a few people have proposed geoengineering methods such as injecting sulfate aerosols into the atmosphere to help cool the planet and counter the effects of climate change. What are your views on those ideas?
Okay, 2 points. First, my views, yes. I think it is all right, and the scientific community should carry out the research. Okay. But I also agree with the consensus that before we actually implement these measures, we need to consult, just like we do with the United Nations, with some international changes. Since you are going to affect the entire planet, it's not something that your scientists should decide. The worry being that you might have some unwanted side consequences, okay? What will those be? But yes, you just have to keep learning. I just want to stress the point that particular geoengineering solution was suggested, and it's been advised by Paul Crutzen, by my colleague with whom we share the Nobel Prize. And I understand some of his points, namely that you can put relatively cheaply sulfur particles in the stratosphere, just like some volcanoes do. And we know that the temperature drops when volcanoes explode vertically, because most of them don't. But if they do and inject in the stratosphere, temperature drops. So that's happened historically. They drop 1 or 2 degrees just by 1 year. And the point being, if something goes terribly wrong, you just stop that, and it's not something that is going to last forever. But I guess the counterpoint is, look, it's not that difficult. It goes counter, I guess, or it's connected to the previous question. We have other solutions. Just reduce emissions. And those, we know that that's a natural way of doing that. There are people suggesting yet other kinds of solutions, which is to capture CO2 in the atmosphere, but that's very expensive at the moment. Maybe in the future there will be ways. By the way, there is also now a trend. It's fusion. For many years, fusion was 50 years in the future, no matter when you were talking about it, always 50 years in the future. But now there are some findings. Again, MIT has made a lot of progress here because they can have huge magnetic fields in a very small volume. And the idea is that not next year, but within a decade, we might very well finally see fusion coming around. That would be, imagine if you have a solution of that type without adverse consequences, then you would not need geoengineering. But by all means, let's keep exploring that, just if it becomes really necessary.
Thank you. Question here, please.
So I've encountered, unfortunately, individuals who would think that, a few changes in temperature or Celsius wouldn't make such a difference. How do you approach responding to someone to get them to grasp the importance of even a few degrees? Well,
you show them some of the consequences that we're already having. It's not just a few degrees that matter. In fact, we acknowledge that in some places on the planet, you will have some benefits. But what we have seen just in the last few years is very clear examples of negative consequences. And you can cite many examples. Among them, that glaciers in the mountains are melting. Okay. Now, in principle, you won't be able to do tourism over there and look at the nice pieces of ice. So what? No. This matters because that's a very important water source for agriculture in some places. Or what happens is if the rainy season in India changes completely and they won't be able to do agriculture the way they are doing. So it's a change. Part of the explanation is that society, civilization, and so on, has grown in the Holocene with very few climatic changes. Okay? And if we have changes that are happening very fast, it's a change itself that gives us trouble. If the temperature had been a few degrees warmer for tens of thousands of years, civilization would have probably evolved in a different way. But the change and the unknown non-linearities that if you are scientists, you probably know that you suddenly reach a threshold and suddenly things change, not smoothly, but suddenly, okay? The main difficulty here, because of the complexity of the climate, is that it's very hard to predict what these so-called surprises, okay? So that you would have just to show them by example. And that's one disadvantage of condensing the conversation just in the 2 degrees or in the temperature change. It's just one way to illustrate. But I would emphasize it's an oversimplification to talk just about this surface temperature change. That's just one way to summarize issues, but it's not the main worry.
Thank you. Please.
Thank you so much for the great lecture. One thread that I hear that is common to yesterday's discussion and to your lecture today is that our greatest challenges are not scientific and technological. They are political and cultural.
Right.
Would you agree that we need more grand challenge initiatives that address politics and culture?
Yes, very much so. And let me give you two sort of ways in which we can do that. One way is extremely important, unfortunately not very fast, but nevertheless terribly important, and that's a change in education. Because we have now new ways to educate, starting with elementary school, how children learn science. And there are new ways to do that in which they learn it very much faster, much more efficiently, and not only does it work much better, it's much more entertaining. Okay, so you get the children to really enjoy doing science, but other subjects as well. How? Because it's the so-called active or interactive learning. And that happens also in college. It happens at all levels, but in college, instead of just listening to somebody, you actually discuss, you form groups, and so on. It's a long story, but that's happening already at MIT and Harvard. There are some of these courses. And the most important thing is that in this fashion, you can also talk about values. Okay? Children learn to appreciate nature. Then they go back to their homes, and they are the ones telling their parents to not to waste energy, for example, okay? Because they love nature if they are properly educated. And so one big expectation is that the new generation, the younger generation, when they get, where they need to get eventually the decision makers and so on, they will be much more responsible, because an important value is let's all work together and make sure that we do things that not just for our own personal benefit, but for society at large. Okay, so that's one way, but I understand that will take some time, but it's no longer waiting 3 or 4 generations. But the other way is we're making some progress. So when we talk to politicians and we sit down with them and so on, with many of them things work. We were talking about people in government. We have Republicans. What is amazing is Republicans from past administrations, I have many good friends, they are very eager to change. They just cannot convince many of their fellow Republicans that are currently in Congress, okay? But they are changing already, okay? Things are beginning to be so clear that that's changing. It's not changing at the level of the presidency yet, okay? But hopefully that's temporary. But the Republican Party, as you know, is changing. So we think we can do it because it makes so much sense. Okay? And because we can actually put it very clearly on the table. What are the reasons that you don't want to do it? We know the Tea Party initially, the reason was we don't want government interaction with anything. And so anything such as climate change, we should just discredit. But that's exaggerated. Obviously, the government needs to help with some measures, such as the example I always put on the table, which is obvious now, is the government is the one responsible for removing lead in gasoline. And we say, no, the government shouldn't touch what the private industry is doing. How many children would have died without that type of government action? And now air quality in many developing countries. Many people would die if the government just says, no, I will let the private sector do what they need to do. No, it's very clear that government should act, but it should do it appropriately, getting the sectors that are affected involved in the decisions and whatnot. I hope, I'm an optimist, and I think, well, nothing less than the Paris Accord, okay? Well, I'm biased because I was in PICAS, which is the President's Council of Advisors in Science and Technology. So I worked with President Obama. Okay, there were 20 of us, and a few of us there were climate change sort of scientists, and we talked to him many times and defined essentially the Paris Agreement. What do I mean? It was defined in such a way that the United States could pass it. What did that mean? That meant that U.S. Congress had nothing to do with the Paris Agreement because they would not have agreed with it. Okay? But that's changing now, we hope.
Thank you. Another question, please.
So a lot of experts agree that agriculture is one of the largest global emitters of greenhouse gases, and not only in that respect, but also a huge waste of water, the use of pesticides and fertilizers. Some of these experts agree that a change to permaculture might be a solution to fixing that part of the greenhouse gas emissions issue. So to what extent do you think that collaboration between agriculture scientists and climate scientists, as well as other changes, for example, turning to indigenous cultures for knowledge on how nature works, without necessarily the rigor of scientific investigation, but just inherent knowledge of how these systems work?
Well, I think you can mix that. You can, if you have some ideas about some changes in agriculture, you can do scientific tests. And that has happened, so it need not be incompatible. But that's a recognized aspect of climate change. It's not necessarily the largest or the most important because it's, again, burning fossil fuels. But agricultural practices have been part of this whole idea. And in fact, at PICAS, I was just talking about this group with President Obama, we have, if not one, maybe two reports on agriculture where we met with experts, some actually from this university that were very much experts on these issues. And yes, there are problems, excess use of fertilizants, okay, that affects the nitrogen cycle and so on, so that should be improved. But it's even more important in developing countries where they're just wasting resources, okay. So there is a lot that can be done with agriculture to improve the practices. And again, it's a huge challenge, not just because of climate change, but because you have to feed a growing population. Okay? But fortunately, I think there's good science in that field, which is far from my own field, but as I understand, there is progress. But there again, the politics remains to be worked out. And just give you one example, which is in Mexico, where we deal with science policy. And one of the things we're trying to change, we have not succeeded yet, is there is an incentive in agriculture where the government simply gives away water and electricity. And that's not very wise, because then people in business, and so they don't care. They can waste water and electricity, government pays for it. Why should we care? So we are suggesting to change the subsidy, not to remove it, but to give them the resources in cash or in some other way, but so that they don't just waste the water and the energy. And so there are many examples like this here and in the developing world that need to be changed with the help of science. But again, we're talking a little bit about the politics, the science and the technology.
Thank you. A quick question from this side first, please.
Naomi Klein in This Changes Everything says that it's capitalism versus the climate. And since emissions have really increased under this deregulated capitalism and a lot of industry is just not regulated or punished for its over-emitting, do you think that we can really make progress without changing like the economic system?
That's a good question. And I think, let me be very optimistic, I think we can, because capitalism is the only form of I guess, of government that we know works. Has many problems, okay? But we know that, for example, the Soviet Union didn't work out before, so and Venezuela is not working at all, and so on. So other systems have big problems. But capitalism, if it's properly managed, if you have the population well informed and the politicians responding to that, we believe it can be done, and we have many examples of industries here in the United States that are socially responsible and acknowledge you can make money and still you can protect the environment and you can make sure that you're not doing damage to future generations. It's possible, but we need to work together, okay? And that's what we should do. Yeah.
Having spent 48 hours standing next to you, I think optimism is the word that best defines you. You are the most optimistic laureate I've ever met. It's fantastic. Please, next question.
So a big thing I've picked up on here is that there are a lot of political issues back behind this, that the science is there, but the politics isn't quite there. We need to be optimistic about it, but how do we get governments to go along with climate change? How do we get people to rally behind it, like you got people to rally behind the ban of CFCs?
Well, we almost did it. We just have, I think, a temporal problem now here in the States. But with the Montreal Protocol, I was there. We were able to make it. It worked. It happened. All the countries in the world accepted. Margaret Thatcher, who, by the way, she was a pharmaceutical chemist, okay? So she was a scientist, but she very much initially was a little opposed until she understood everything, and then with Ronald Reagan, they did it. Very conservative governments at that time. Let's talk about climate change. In Paris, because that was still with President Obama, but I was able to shake hands with lots of heads of states. They all took a photograph, 150, I don't know how many of them, and they all agreed. So it can be done, okay? One trick is to go to high levels. But unfortunately, there are exceptions. We just have to be optimistic, and we have to keep working. You can argue and say, oh, society will evolve, civilization will advance, no matter what. Let's just wait. No, I would say that's all right, but it won't happen by itself. We need to be there. We need to work. We need to work all together, and I think we can do it. Okay? That's my optimism.
Thank you so much. I think we should stop there and summarize your whole approach as keep working, it can be done. That's right. And that seems an appropriate place to stop. So I'd like to thank you very much indeed, Mario, for everything you put into this and the audience too.
Thank you very much.